Okay, so now you're back from the little exercise of writing out the tables for Mod 6. This is also on the homework. So as you can see, I've got them up here. And what I want to do is to let's look at these tables a little bit and see what does that prompt for us. So first thing you notice immediately is that if you're looking at the tables for addition, that every single row is basically the numbers in order, just shifted. So you have 0, 1, 2, 3, 4, 5, and then you have shifted over by 1, 1, 2, 3, 4, 5, then 0, then shifted over again by 1, 2, 3, 4, 5, 0, 1. So it's like a cyclical shift. And that's exactly what we expect, right? This is, after all, moving on a circle, and this, when you have 0, you look on the circle this way, 0, 1, 2, 3, 4, 5. And when you start with a plus, you can think of that as starting in a different place. You start here, 1, 2, 3, 4, 5, 0. So the addition is very simple and easy to understand. Multiplication, on the other hand, is a little bit more interesting. So you look at multiplication and you notice that, well, 0, of course, is always 0. No matter how you look at it, 0 times anything is 0. But here, we really have like 3 different kinds of things that are going on. First, you have these all 0 rows. And then you have these two right here. And these two have all the numbers in them, just in a different order. All the numbers are there. And then you have in here, you have different kinds where some numbers are missing. So for example, for 2, we have 0, 2, 4, 0, 2, 4. And there's no 1, there's no 3, there's no 5. Only half the numbers are here. And similarly for 4. So you have these two, both of which are kind of periodic and have period 3. So these guys have period 3. And so they're not actually including all the numbers. They're including only a subset of the numbers. And then you have this one here, which is even simpler. It's just 0, 3, 0, 3, 0, 3. So this one is also periodic, but it has period 2. So we have all zeros, then ones that are not periodic at all. All the numbers are there, all the numbers are there. And then these ones here, which are actually periodic with period 3, and then one with period 2. So these are some different kinds of things that are showing up in the multiplication table, and we should try to understand why. But before we do that, I want to define the idea of congruence, which comes from another way of interpreting what we've been doing so far with the numbers in a circle. So one way of thinking about the numbers in a circle is that we started here at 0, went 1, 2, 3, 4, 5, and then 6 is the same as 0. So we can actually write a little 6 here and say 6 is the same as 0, and then 7 is the same as 1, and then 8 is the same as 2, and then 9 is the same as 3, and 10 is the same as 4, and 11 is the same as 5, and then 12 is again the same as 6. And so what you can imagine here is that we have 13. We get all these numbers that we can arrange in this circle, and a whole bunch of numbers are the same. So this is how we define congruence. Congruence means two numbers are congruent if they're equal to the same thing mod something. So we say A equals B mod M. This is the same as saying A is congruent to B. Mod M. And this means that A equals B plus K times M, where K is some integer. A equals B mod M if and only if A equals B plus K times M. So the two numbers are relatable to each other through a multiple of m. So here we have mod 6, so 0 and 6 are related to each other through a multiple of 6, an additive multiple. You add together something that's a multiple of 6. Another way of thinking about this, about congruence, is to look at the difference. We say a minus b is a multiple of m, or in other words, m divides a minus b. All three of these definitions are the same. A equals b mod m is the same as a equals b plus km. It means a equals b plus km for some k, where k is some integer. It is also the same as saying a minus b is a multiple of m. Right? Bring the b over to the other side, you'll see a minus b is a multiple of m. Or, alternatively, m divides a minus b. These are all definitions of congruence. So, when we were talking about that rule for how it is possible to calculate things in mod m, for any m, that can be expressed in terms of congruence as a theorem. So the theorem says if a equals b mod m and c equals d mod m, then a plus c equals b plus d mod m, and a times c equals b times d mod m. Now, the notes have a proof for addition, so I thought I'd just quickly write out a proof for multiplication, just so you can see how that's done. So how do you prove it for multiplication? So we're trying to prove this statement. So first we say, okay, if a equals b mod m, this is the same as saying that a equals b plus km, right? That there exists some k for which this is true. If c equals d, that's the same as saying that c equals d plus k prime m, some other k prime. So now we know these two things are true. So now we just write out what we want. A times c equals b plus km times d plus k prime m, which is b times d plus m times, let's look at this m term, so b times d. Let's look at those terms that have m's in them. So we have dk plus bk prime plus k prime m. Right, I just did the multiplication out. And we notice that all of this is clearly a multiple of m. So that means a times c equals b times d plus a multiple of m. But that's the same thing as saying that a times c equals b times d mod m. The two have to be the same.